And we're just busy doing this example, and I'll finish off this example first thing today. But what we're going to talk about for the rest of today's lecture are bases. What does it mean when we say that a set is a basis for a vector space or a basis for a subspace? And then we'll see that from this notion of basis, we can very easily or very naturally define the idea of a dimension. And that's what we'll get on tomorrow, and we'll see that the sort of formal definition that we put up of dimension is going to agree with our intuitive sort of thoughts or intuitive ideas about dimensions of various spaces. So we'll see, for example, that R2, our formal definition, is going to say that R2 is a two-dimensional space, and R3 is a three-dimensional space, and that all seems very reasonable. But let's actually finish off this example. This is the example that we were looking at the end of yesterday's lecture. We have this set here of three vectors. In this particular case, the vectors are polynomials, and I guess this is really something which is a little bit naughty. This should be independent on R. If you're talking about dependence or independence of functions, it's always on some interval, yes.
At the end where you said that the solution is linearly dependent.
Yes.
If you wrote that, so what if you wrote that equation, or if you wrote the other one which had the variables alpha, beta, and gamma, would they both suffice for you?
Yeah, okay, I'll come to that at the end. Okay, so what we're trying to do here is we are interested in this this expression up here, let's call it star. We're interested in the solutions to that equation star. Right? We've got alpha times by the first vector plus beta times by the second vector plus gamma times by the third vector. And the question we're asking is, are there solutions other than just alpha is equal to beta is equal to gamma is equal to 0? Obviously, if you set alpha is equal to beta is equal to gamma is equal to 0, that must hold because you get 0 times by 0, 0 plus 0 plus 0 is equal to 0, which is great. But we want to know if there are other solutions. So what I've done in the next line is I've just rearranged it. So we've got all the x squared terms together, all the x terms together, and all the constant terms together. And what we saw yesterday was that x squared, x, and the constants are linearly independent of each other, which means that the only way that this alpha plus 2 beta plus gamma x squared plus alpha plus 3 beta x plus minus alpha plus beta minus 4 gamma, the only way that that thing can be equal to 0 is if each of those coefficients, the coefficient in front of the x squared and the coefficient in front of the x and the constant, are independently equal to 0. So each of those is independently equal to 0, so we end up with three equations here. So we've got three rows in our augmented matrix. Each row in the augmented matrix corresponds to a different power of x, and each column in the augmented matrix corresponds to one of these unknowns, alpha, beta, or gamma. And we do a little bit of Gauss reduction, and after two steps of Gauss reduction, we get this augmented matrix over here, and we can see that we've got three columns, three unknowns, but only two pivots. So there's a column which is missing a pivot, which means that we would let that variable gamma be equal to t or s or p or whatever. It's a free variable, but this means that there are an infinite number of solutions, right? So there are an infinite number of solutions to this equation star up there. In particular, this is just one of them that I've written down, right? We could have alpha is equal to 3, and beta is equal to -1, and gamma is equal to -1, right? As soon as we find one solution, we actually know that there must be infinitely many because we could just scale this. You could make this a 6, and this a -2, and that a -2. But the point is we have a non-trivial solution, and that's sufficient for us to say that the set must be a linearly dependent set. All right. Yeah, so that I think is about that for linear independence or dependence. And we're going to move now to a discussion of bases. Okay, so bases. That's the plural form. The singular form is basis, but let's write up a definition for a basis. So a basis, and a basis will always be a basis for something, right? It'll be a basis for a vector space. or for a subspace. So we've got a basis for a vector space or a subspace is a set which satisfies two conditions. Is a set which, one, must be linearly independent, and two, must generate that entire vector space or that entire subspace. Okay, so which one generates the vector space, and two is linearly independent. Okay. So we need these two conditions to hold for a set to be a basis. So a basis is just a sort of, in some sense, a very special generating set. It's a generating set which also is linearly independent. So what we're going to do now is just think about some pretty simple examples and try to convince ourselves that certain sets are actually bases. And I guess basis is the singular and bases are the plural forms. But certain sets are bases for particular vector spaces. We'll take a look at this first very simple example. Okay, we're going to show that 1, 0, and 0, 1. This is a set here with two elements. We're going to show that this set is a basis for R2. So we've got to check two things. We've got to check that it generates the entire vector space, and then we've got to check that it's linearly independent. And most of the time it's easier to do it in this way, because then we can reuse some of our calculations for part 1 when we get to part 2. Okay. I want to show that this is a basis for R2. So the first thing that we have to show is we've got to show that this over here generates the whole of R2. Another way of saying that is that if I take an arbitrary vector in R2, so I just take the vector xy could be anything, I take the arbitrary vector xy, I should be able to write it as a linear combination of those two vectors. And it's pretty easy to see how we're going to do that. We're going to say, well, xy is just going to be x times by 1, 0, plus y times by 0, 1. Right? So because this is such a simple looking thing, we can maybe just write down the answer immediately, but let's do it a little bit more rigorously. Okay. So that we've got something that we can generalize to more difficult examples. Okay. So first, or 1, we show that this set over here we're going to show that this generates R2. So we take a vector in R2. We take an arbitrary vector in R2. So consider xy is an element of R2. So we've taken an arbitrary vector in R2. We haven't imposed any conditions on x or on y. I mean, I guess we should impose some condition on them, which is just that x and y are real numbers. They can't be complex numbers, and they wouldn't be in R2. But we haven't said that there's any relationship between x and y. We can choose x and y freely from any of the real numbers. So this is really just an arbitrary vector. So what we want to show is we want to show that there are some values, alpha and beta, so that we can write down xy is equal to alpha 1, 0 plus beta 0, 1. So are the values alpha and beta such that xy is equal to alpha 1, 0 plus beta 0, 1. Okay. And I mean, I'm being very sort of verbose here and writing down a lot of stuff. Maybe it seems obvious to you what the answer is, and it should seem obvious because it's a simple problem, but we'll get to more complicated problems where being verbose is a good thing. So what we're interested in is finding values for alpha and beta, and what we would do is we would write down an augmented matrix like this, right? So we'd write down 1, 0, 0, 1, x, y in general, and then we would Gauss reduce it, right? This matrix is already actually Gauss reduced because the sort of tentative basis that we started with was so simple. Okay, so in principle, so in a more complicated example, so in a more complicated example, we'd actually have to do some Gauss reduction. But this is so simple that this is already as Gauss reduced as it's going to be, and we can immediately read off the answers. We have alpha is equal to x and beta is equal to y. So this implies alpha is equal to x and beta is equal to y, which is just saying that xy can be written as x times by 1, 0 plus y times by 0, 1. Okay. So an arbitrary vector xy can be written as a linear combination of 1, 0 and 0, 1 in the following way. And we can conclude that this set here generates R2. So is everyone happy with what we've done here in this first part of the problem? We've shown that this set 1, 0, 0, 1 generates all of R2. Is everyone clear with this? Okay. So the next thing that we have to do is we've got to show that this set is a linearly independent set of vectors. Okay, so that's the second thing we've got to show. A basis has got to generate the whole vector space or the whole subspace, and it's also got to be linearly independent. So the second thing we've got to check is linear independence. Okay, I did put that in a little round bracket like this. Okay, so now we check for linear independence. Next we check for linear independence, and we basically just reuse the calculation that we've already done. We've done the calculation above here. We may have done a Gauss reduction if this was a more complicated example, but we've done a calculation to find out if an arbitrary vector xy can be written as alpha times by the first vector plus beta times by the second vector. So we use that calculation, but now instead of taking an arbitrary vector xy, we set x is equal to 0 and y is equal to 0, right? We just check if it generates, we just check how it may generate the 0 vector. So the quickest thing to do is we reuse our calculations. We use the calculations above. Take x is equal to y is equal to 0. And that tells us that 0, 0 is 0 times by 1, 0 plus 0 times by 0, 1. Right? So that's the only solution that works. There was a unique solution when we did this Gauss reduction because we had 2 unknowns and 2 pivots. So this is the only solution that works. This is the only solution that works. Which implies that this set over here is linearly independent. And we've now shown that it generates all of R2, and it's linearly independent, so we would call this set a basis for R2. So this set okay. Are there any questions about this? I mean, this was a pretty straightforward, pretty simple example. Okay. I mean, this was a pretty simple and straightforward example. It's so simple and so straightforward that we give this set over here a special name. We would call this the standard basis, or possibly the canonical basis. Those are two different terms that we'd use, the standard basis or the canonical basis for R2. Okay, and this is, let's just say this is our definition. That's set as a standard or canonical basis for R2, and we sometimes use the following notation to refer to the vectors in the standard basis. We just use an E with the subscript 1 to represent 1, 0, and an E with the subscript 2 to represent 0, 1. We denote 1, 0 by, so that E1 means the first canonical basis vector, and 0, 1 by E2. Yes?
What if 3 by 3 identity matrix generates all of R3?
Yes and no. I'm saying yes because your idea is right, and no because the way you phrased that question is wrong. The set whose columns constitute the 3 by 3 identity matrix, that would generate all of R3. The matrix can't generate all of R3 because the things in R3 must be vectors, and the vectors that you want to use are the columns of the identity matrix. Yes. Okay. And so the next question I was going to ask, which has now sort of been, I don't know, foreseen in some sense, I'd like you to write down the canonical basis for R3 and for R4. Yeah.
Does canonical or standard mean that it's in its simplest form?
Well, we haven't defined what something means, what the term simplest form means.
Like, that it would make up the identity matrix?
Yeah, sure. You can say that canonical means the columns of an appropriate identity matrix. Okay, there's no reason for us to take particularly long to do this. So the canonical basis for R3 would be something like this. And let me write it down like this first. You would just write down E1, E2, E3. And that would just be 1, 0, 0. That would be our E1, 0, 1, 0, 0, 0, 1. Okay, so that's the canonical basis for R3. and R4. Okay, we'll need a little bit of space, I guess. This line will work. One zero 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 0 1 0 0 0 0 1 0 0 0 0 1. All right. Did everyone write down something like this? Did everyone write down exactly this? Yeah, pretty much, right? Okay, so these are the canonical bases for R3 and R4, and you can extend this in the obvious way to RK. Right, it'll be a set E1 all the way up to EK, where E with the subscript J just means that the jth entry is equal to 1, and all the other entries are equal to 0, right? So yeah, we can very easily extend this and understand the canonical basis for R3, R4, R5, and so on. Okay. Let's take a look at a more complicated, or not really much more complicated, but a slightly trickier version of the first problem that we did today. Right? So we looked at this set over here, the set 1001, and we showed that this was a basis for R2. I'm going to give you another set of 2 vectors, and you're going to show that it's a basis for R2, but it's not going to be quite so neat this time. Right. So we're going to show that, and let's actually give this a name so that we can talk about it later. Let's call it B for basis. Show that this over here, show that B, which is the set of 2 vectors 1, 2, and 3, 5. Show that that set B is a basis for R2. And you can take 5 minutes to do this, and I'll walk around. If you want some help getting started, just stick up your hand. But basically, you're going to do exactly the same thing that we did in the previous example. You've got to show that this set over here generates all of R2. You've got to show that this set over here is a linearly independent set, and that's enough to show that it's a basis. It's pretty straightforward. The only difference is that over here, we're going to have to do a tiny bit of Gauss reduction, which we didn't have to do in the previous case. Going to check whether or not this set B, 1, 2, 3, 5, generates all of R2. Right? So we take some arbitrary point xy, some arbitrary vector in R2, and we want to know if xy can be written as a linear combination of these two vectors. So xy is equal to alpha 1, 2 plus beta 3, 5. And this is the corresponding automated system over here. So each column here corresponds to the variable alpha and beta. And we Gauss reduce it. This is the first step. We've subtracted, okay, hold on. Let me write this here, since it would be sort of hypocritical for me, because I'm going to insist in the test that you write down what your row operations are. So I should write down what mine are. Row 2 minus 2 row 1. Okay, so we've taken row 2 and subtracted 2 copies of row 1. Then we've taken row 2 and we've scaled it like that. And then we've taken row 1 and we've subtracted 3 row 2. But we do this Gauss reduction. And the important thing when we do this Gauss reduction is that we find a system which is consistent. Right? It's consistent, which means that we can rewrite xy as a linear combination of these two vectors 1, 2, and 3, 5. And in fact, the appropriate coefficients are just 3y minus 5x and 2x minus y. And what this is telling you is that, for example, let's just maybe put this in as an aside. For example, you could take the point and you pick any point here. Give me an x value. 3. Y value? 24. No, that's too big. Give me a smaller y value. 7. Okay. We can take the point 3, 7, and if we were to take this now, so 3 times y, that's 21 minus 15 times by 1, 2. And over here we get 2x, that'll be 6 minus 7, 3, 5. Let's just check what we have here. 21 minus 15 is 6. we get 6 times by 1, 2, plus, okay, and that'll be, dropped a bracket there, that'll be minus 1, so let's just make that minus 3, 5. And if we think about this, what do we get? Our x component, 6 times by 1 is 6. 6 minus 3 is 3, okay, which is what we had. 6 times by 2 is 12. 12 minus 5 is 7. Oh, all right, okay, so we see that this really does work. We could take an arbitrary point xy, any old point xy, and we can write it as a linear combination of these two vectors just by using these coefficients that we've calculated. Well, I mean, no, this is... We wouldn't actually need to do this at all, right? That sort of choice of just using AB we've already done by just using XY. This is really just an illustration of, a specific illustration of the more general fact that we've proved. Okay. The next thing that we would have to do is we would have to show that the set is a linearly independent set, right? So is B linearly independent? So we want to know if we take alpha times by the first vector plus beta times by the second vector and we set this equal to 0, 0, what values of alpha and beta work? Is it only 0, 0 for alpha and beta, or is there maybe some other solution? Well, quickest thing to do is just, well, we take 0, 0 is equal to 3 times by 0 minus 5 times by 0 times by 1, 2, plus 2 times by 0 minus 0, 3, 5. All right, so that's, okay, that's 0 times by 1, 2, plus 0 times by 3, 5. And that was the only solution that we found. So B is linearly independent. We could actually have concluded this a little bit earlier on in our problem. Basically, whenever we have a situation when we do the Gauss reduction up here, and we end up with, we've got no missing pivots, and we have a consistent system, we know that we have a unique solution. We've got a unique solution, so we know that when we go and look for the solution specifically adding up to 0, we'll get a unique solution, right? But that's, I guess, just something we've written down here in more detail. This is the only solution, so it's linearly independent, which is then telling us that, therefore, B is a basis for R2. Okay. So we've seen at least 2 different bases for R2. We've seen this standard basis, canonical basis 1, 0, 0, 1, and we've just found a second basis, which was the basis 1, 2, 3, 5. Could anyone suggest, maybe not a specific set of vectors, maybe that's a little bit putting you on the spot, but another basis? Could you think of another basis that might work for R2, if you can find some sort of characterization of it? So any linear combinations of those two? 2, 0, 0, 5. Okay, sure, that works. Okay. What else? I mean, geometrically, can we think a little bit about how many vectors should we have in this basis? 2, right? Should we? And will any 2 vectors do? No, right? You can't have vectors which are parallel to each other. Okay. So we're actually going to be able to find an infinite number of bases for R2, but they're going to have something in common. All the bases for R2 will have exactly 2 vectors in them, and these vectors will point, they won't be collinear vectors, right? They'll point sort of, in some sense, in different directions. Okay, and we can generate an infinite number of bases like this, but they're all going to have 2 elements in them. And this is important. This is what we're going to get to. We'll do some of it now, and we'll get to the rest of it tomorrow. This is how we're going to define the dimension of a vector space, or the dimension of a subspace. It's going to be the number of elements in a basis. And we can just use any old basis because all bases will have the same number of elements in them. So we'll say that R2 is a two-dimensional space because any basis for R2 has two elements in it. So I've talked for a bit. Let's start writing some of this down. Okay. There are an infinite number of bases. There are an infinite number of bases an infinite number of bases for R2. All the bases are sets of two, let's say, non-collinear sets of two non-collinear vectors. That's just a fancy way of saying that the vectors can't point in the same direction. They must point in different directions. And let's see if we can just think, maybe sort of formalize this a little bit, explain why this is the case. Okay. Sets of all the bases of R2 have two elements. That's sort of the important point. And let's think about what might happen in the case where we've got one element and how that would fail to be a basis, and where we've got three elements and how that might fail to be a basis. Okay, so could a one element set be a basis could a one element set be a basis of R2? And we said no, right? A one element set, if you think about what just one vector, what does one vector generate? It just generates a straight line pointing in this direction. Or if it was the zero vector to start with, then it just generates a point. But it fails to generate all of R2. Right? So can a one element set be a basis for R2? No. No, it generates either a point or a line. It can't generate all of R2. What about a three-element set? Could a three-element set be a basis for R2? Any suggestions on this? No, someone else.
For some solutions of the three-element set, it could generate composite R2, but it could also generate composite R3.
Okay, so you're right that it could generate all of R2. So the three-element set is not going to fail to be a basis because of problems with what it generates. But it might fail to be a basis in some other way. Okay, sure. So a three-element set is going to be linearly dependent. Why?
Because if the other two elements can generate the whole R2, then they can generate the third element.
Okay, sure. That's the right sort of idea.
Two vectors could be a linear combination.
Two could be a linear combination of the others.
When else is the matrix that you have three unknowns, then it was
That's exactly right. Okay, so that's maybe the easiest way to see it. We're going to set up a Gauss reduction, and there'll be 3 columns. One column for each unknown in front of these 3 vectors, alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. But there are only 2 rows in this matrix, which means that you can have at most 2 pivots. So at least one of the variables will be a free variable, so you'll have an infinite number of solutions, so we have a linearly dependent set of vectors. Okay, so could a 3-element set be a basis for R3? No. It must be linearly dependent. Right? And the reason for that is if we have something like this alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equal to 0, this becomes, and let's not worry too much about what these entries are. Right? But the shape of the matrix is the following. Right? That's the shape of the augmented matrix. And we can have at most 2 pivots, but we have 3 rows. Sorry, at most 2 pivots, but we have 3 columns. So at most 2 pivots, but we have here 1, 2, 3 columns, and that implies infinite many solutions. So linearly dependent. Okay. And this is something which is we're going to see more generally. If you've got an n-dimensional vector space, any set of more than n vectors will be linearly dependent. Any set of more than n vectors will be linearly dependent. So if you've got a set of 6 vectors in R5, you don't have to do any calculations to decide if it's linearly independent or dependent. It's linearly dependent. There are just too many vectors in that set, right? But we'll get to all of this in the next couple of lectures, so I suppose we'll stop here a couple of minutes early. If you've got any questions, you can come and speak to me at the front.